Welcome to lesson 6 of unit 7. So we're getting close to the end and we're looking at analyzing logarithmic functions. So remembering that when we just have the word log, it is assumed that it's base 10 even if it's not written. So we can use our calculators to just plug it in and evaluate them. So if you take a second right now, double check that you know how to use these. We've got log 10 of 4 and log 10 of 34. So try punching that in. So when I punch those in, you should get these two values. Okay. When the base is not 10, we need to use a change of base formula. And that is what you're seeing right here. So change of base means that we take whatever the value was and we take the log of that divided by the log of the actual base that was written there previously. This lets us evaluate ones that we can't punch into our calculator. So we've got log of 50 divided by log of 5. Now, you might look at this and be like, Miss Conrad, why can't we go log 50 minus log 5? And you're thinking back to our last lesson and looking at the quotient rule. The problem is that these values are separate and the log functions are separate. So we can't just do that. This has a specific value and this has a specific value, and they're not associated together. So we can't use our quotient rule. Quotient rule would only apply if we had something written like 50 over 5. And we wouldn't even have that because we would simplify it to 10, but this is what we would need to punch into our calculator. So when you go to punch this in, make sure again that we're closing brackets. If your calculator opens with an open bracket here, make sure you close it off before hitting divide so that we don't end up with log of a log somewhere in there. So if you want to give that a shot, and if you want to try B, give those a go before we move on. Okay, and so when using your calculator, you should get those values. Good to go. So I'm going to switch these letters up like I did before to reflect how we used them previously. So you can do the same if you want so that you know exactly what's included and in reference to our transformations unit before. So this is D, A, I'm going to change the base to N. This is B, and this is C. Okay, so A will cause a vertical stretch or compression. B will cause a horizontal stretch or compression. D will cause a vertical translation, and C will cause a horizontal translation. And when not D and C, A and B are negative, we'll get some reflections going on. So again, now that we've changed those letters, that accurately reflects kind of what we talked about in our transformations unit. So applying that, create a table of values for y equals log of 2x. So we'll start with that. X, y, log 2x. Okay, so I'm going to be very intentional in my values. I can't make something to the power of something else equal 0, so I'm not going to use 0, but I can use a quarter. And that would be 2 to the power of negative 2. I'll use a half, so that's 2 to the power of negative 1. I can use 1, that would be 2 to the power of 0. Use 2, which would be 2 to the power of 1, and 4, which would be 2 to the power of positive 2. So that's my table of values for y equals log base 2 of x. So if we then considered this graph in relation to this one, what would happen? And again, another thing we can do up here, we really want to make it look like our transformation notation, is put the plus D on the outside and put square brackets around this part. Okay, so sorry about that. changes that need to be made. Okay, so if I look at this value is just my base, and that's fine. That kind of goes with this. This 2 here is my B value. And so again, remembering way back from their transformation unit, that is a horizontal compression by 2 or half. We're squishing it in. So what I would expect to happen is that any values that are not on my y-axis, which is everything, is going to be shrunk by half. Okay, when I'm doing my mapping notation. This -1, because it's outside of the brackets, it's completely separate. I can imagine that this is what I'm taking the log of, is just this 2x, and subtracting 1 after, which means it's my vertical shift. So it would be y -1. So that, again, going back to that mapping notation that we saw a long time ago. So what would that look like now? Well, if this was our y equals log base 2 of x, my y equals log base 2 of 2x minus 1 would give me a very different table. And how I'm going to do that is I'm going to change my x's by multiplying by them by half. So 8 1/8, a quarter, a half, 1 and 2 is how my x changes based on this. My y is going to go down by 1, so -3, -2, -1, 0, and 1 are what those points are going to look like. So if I want to sketch these two, I'm going to just use 2 different colors. I'm going to do this first one in purple, and I'm going to be very specific on how I make my axes. Do them in black, since I have to bear in mind how far I'm going for both of them. So because I go all the way down to -3 in terms of my values in that second one, I'm going to make sure that I go down to -3 on my y-axis. And because I go up to 4 in my x's in this first graph, I'm going to be intentional about that too. So make sure I get to 4 on my x-axis. 2, 3. And these will be nice because I can even subdivide them in half. Help me sketch in all these fractions that I've got eventually. So once I've got that, I can do both my graphs. So a quarter and -2, half and -1, 1 and 0, which is again my expected point for any basic logarithmic function, 2 and 1, and 4 and 2. So again, my vertical asymptote is here at y equals 0, or x equals 0. My x-intercept is at 1, and I'm not going to have a y-intercept because of where my asymptote is. So my domain for that function is from 0 to positive infinity, only going to the right. My range is from negative infinity, because it goes down forever, to positive infinity. Answering part C. Okay. My second graph is going to look a little bit different, but I've got my coordinate points because I used that mapping notation to figure them out, so it makes the life a little bit easier. So I've got 1/8 and -3, so it's going to bring me quite tight in here. Okay, a quarter and -2. Actually, that one didn't change at all, so that's kind of nice. And then I've got half and -1. Let me see, 1 and 0. Sorry, getting ahead of myself. half and -1. So we actually had 2 invariant points on this graph. Which is interesting. And then we've got 1 and 0. And 2 and 1. Excuse me. So this is kind of an interesting impact because just based on the values we chose, each one of them kind of shifted down 1. What's interesting here is that the halves kind of shifted, so it ends up looking very, 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 very similar. And actually, this is probably would have been. And so we see, even though we impacted the b value and squished it down, because the base is actually the same as the coefficient, we don't notice any change. Our values end up being the same. Got points all in the same spots. Our curve ends up being 1 on top of the other. So my domain and range hasn't actually changed. So that's an interesting coincidence. Okay, but again, this only happens very unusual case. Okay, so usually if we change our b value and we change our y vertically, it's not going to end up giving us the exact same graph. But if we look at this one, we'll see a much more significant difference. So in reference to our first graph, again, because we're still working with that base 2, this is y equals log base 2 of x. Okay, using the same points, we've got a quarter, half, 0, 1, and 2. 2 and 4. We're getting -1, negative. Oh, okay. All excited about this, doing it wrong. -2, -1, 1. Trying to do this too fast. There we go. That makes more sense. Okay, so I should have just looked up here and done the same thing. In reference to that, though, this is the important part. We've got a vertical flip because of that negative out in front. And we're also going to have a horizontal shift. And it's going to go not left, which is negative, but because we have to account for that like change in sign, we're going to right 1. So what does that look like? Well, it looks like this in terms of mapping notation. I'm going to go x plus 1 and -y. So if we remember how to do that. So what does that mean in terms of table of values? Well, it means I'm going to add 1 here, so that's going to be 5 quarters, 3 halves, 2, 3, and 4. And these are going to change signs, so it's going to be 2, 1, 0, -1, -2. Once I look at this, then I can graph it. I'm going to sketch in this one again, just kind of as a point of reference, though. So being aware that I need to go up to 4, though, on my x-axis. I only need to go to 2 on my y-axis. This edge looks a little shorter, so I'll use it as my scale maker. Okay, so plotting this first one again, I'm going to do it in purple. Got negative quarter and negative 2. Negative half and negative 1. 1 and 0 as usual. 2 and 1. 4 and 2. Okay. So this is just my y equals log base 2 of x. And the question didn't ask me to graph that, but just so that you have that visual representation, especially since we didn't really see much change in this first graph, I want you to have that in front of you. So what's happening here is we get 5/4 and 2. So we go to 1 1/4 and positive 2. Going to 3/2 or 1 1/2. That's going to be a positive 1. 2 is 0. Okay, so our intercept has changed. 3 and negative 1, 4 and negative 2. And so we can see a couple things. We ended up at the same this should be 5. Sorry, that's my mistake. So that doesn't make any sense. So 5 would be off, so I'm not going to plot that point. And so we're going to end up with a very similar shape because we haven't done any vertical compression or stretch. We haven't done any horizontal compression or stretch. What we see is our graph has shifted over, and instead of our axis being at x equals 0, it's now, our asymptote rather, our asymptote is now here at x equals 1. So that horizontal shift impacts where our asymptote is. And so then all of our points are also shifted over. In terms of my y value, it's just kind of moved things onto opposite sides. So that's why we end up down at the bottom instead of in the positive values. So if you want to pause and give this one a shot on your own, just a quick note that you probably want to move this over onto the other side if you're using that transformation kind of notation that we did in class. Okay, so again, moving that 2 over here allows me to see my vertical shift directly instead of worrying about changing signs. So I know that I've shifted down of 2 and that horizontal reflection. So I'm expecting my graph to be on the left instead of the right, which is kind of unique, not typical of a log function. But one thing to note is that my vertical asymptote stays the same because it lies on my y-axis, which would hypothetically and historically have been an invariant point. So my asymptote behaves just like an invariant point would if it's on the y-axis and it doesn't move. So we've got those two pieces. Again, I wrote the original table of values and mapping notation just kind of as a point of reference. You may have used slightly different points, whatever kind of floats your boat. You could have just chosen random numbers to plug in. That's fine too. However you approach graphing is up to you. I always like using the original parent function just for personal reference. It allows me to apply those transformations so much more easily. So again, if you want to pause and give this one a shot, and again, watch out. The d value is written over here, so if it makes sense to you to move it on to the other side like it does to me, then do that first. So in graphing this one, that shift left of 2, again because of the opposite sign, results in my asymptote being at x equals -2. Then vertically, I'm shifted upward, so all the points that ended up being positives. You would have to use your calculator and that common base to then solve for your x-intercept if you were asked for that detail, so just kind of as a note. Oops. Okay. So our x-intercept is when y equals 0, so we would set this all equal to 0. and I would have to isolate x. So I would do that by moving the 3, and I'm going to also get rid of my common base. I would then multiply by log 2. And at this point, you don't know how to get rid of logs and undo them, but I would rewrite this as an exponent. So we could do that, or inverse log of this. So that would be 10 to the power of -3 log 2 equals x plus 2. And again, I don't expect you to know how to do this yet, but I'll show you just in case. And then we would subtract 2 to isolate x. So this is still coming in our next lessons. And we would get a value there. And it's going to be a number that's like really, really close to -2, but not quite -2, because we can see we're getting pretty close to our asymptote at that point. So just kind of as a heads up, you were not asked for this. You were asked just for your graph. So shifting those points and being able to do that is perfect. If you remember just a key couple of points and are able to, or can generate the parent function original graph, that's going to be your key to being able to draw any log graph, because then we can just apply our transformations from our previous unit. So again, I'm going to post some practice and you'll be able to test this all out, kind of gear our brains up for that final exam while we're refreshing our memory on transformations.